in the
so if you go to github.com libp2p or JS libp2p examples, and then the same for Go libp2p examples.
So we should either choose JS or Go depending on our
yeah, depending, you'll probably get the most out of it when we break out, because we'll be only going through a few of these, but you can feel free to pull it down and go through them as we talk through this. Pick the one that you're most comfortable with, just because we'll be going through a lot of the concepts. So if you work the most in the browser with Go, pick that. So while everybody's doing that, we'll go over some basic concepts and start talking through things. So what is libp2p? So we got the World Wide Web back in '91, which is 28 years ago. And building networking into applications still kind of sucks. If you want to do that distributed or peer-to-peer, it sucks extra hard. So ultimately what we want to do is be able to create a library where we can just pull in the bits that we need for our specific use cases for our applications, and then focus on actually writing our application code and not have to worry about the network stack. So this is ultimately what we're trying to do with libp2p. We're trying to make that easy to just pull in the networking layer and then call it a day. libp2p is the networking layer that IPFS uses. And ultimately, it's just a composable, modular networking library. So if you go to libp2p core, there's usually not a whole lot of logic there, because it's piecemealed in from all of these different modules that you can just bring in and bundle. So what are we building today? So this is the browser version. We're building a chat app. By the end of the course, we'll be using PubSub to go through and send chat messages across to all the available clients. And we have basic chat metrics being passed over PubSub as well to just kind of show connected peers. And you can also, it will be coming up shortly on this slide over here, as peers join the network. Are you connected to the Bootstrap?
I believe so. The connection's pretty slow.
Yeah.
Yes.
Worst case, we'll walk through.
It's not
I'll
like
pull
if
code up.
everybody was not installing things for their own workshop at the same time.
Yeah. All right. So another chat app. Why are we building a chat app? Even a basic chat app is going to let us walk through a lot of the problems that we have with building distributed systems, just connecting to the network. How do we encrypt connections so that we can make sure that our chat data is safe? How do we create our own chat protocol? This is something that a lot of people get hung up on when they're building libp2p, is creating their own protocol. How do we reuse connections? If we want to go through a myriad of using different protocols, DHTs, PubSub, direct messaging, identify, we don't want to create connections to peers every time we do that. We don't want multiple connections to peers, so how do we reuse the connection that we have? We're also going to talk about discovering peers. It doesn't do us very good to be distributed if we can't find peers on the network. And then if we do find peers, how do we connect to them if they're netted? So talking to browsers, talking to people on home networks. A lot of people will, when they're playing around with IPFS, they might do that at home, and most homes are behind nets. So how can we dial those? Handling more complex data on our protocol. We want to be able to have a protocol that does many different things and not just a specific thing. So how can we make our data more complex there? And then we'll also cover broadcasting data with PubSub and how we can find peers and content with the DHT. So there's a lot, but we'll dive in. So the very first thing that we're going to need in order to connect to peers are transports. So libp2p, we use transports to do the actual interface data exchange in libp2p. So transports are going to have two components. They're going to have a dialing component for outbound connections and a listening component. Something important to note, not all transports will be able to listen. This is very common for browsers. However, we do have exceptions to that rule, and we actually have it running today. So I'm running on my machine at this IP address a Bootstrap node that is also running a WebRTC signaling server, which we'll go over what that is in a little bit. But signaling servers and rendezvous servers give us the ability for browser nodes to listen on that server and use that as an entry point so we can kind of overcome that NAT traversal on the browser. So let's look at some of these transports.
This is just a subset of transports we have available. These are some of the more common ones. TCP, we can see its availability here across the different implementations. TCP doesn't work in the browser, unfortunately not yet, but it does work in Node, Go, and Rust, so that's a good option, especially if you're running a server. WebSockets works on all of them, so that's definitely an option to look at. WebRTC is getting an implementation in Go. I don't believe it's quite there yet. And that's nice because WebRTC has some built-in NAT traversal techniques. So once we get that, that will help a lot with network connectivity. And then Quick has a working implementation in Go, but the Quick spec's not complete yet. So we're not going to see a lot of the other implementations until that's done. Although I believe there is a JS version in progress for Quick. All right, so for the workshop today, the transports that we're going to be using TCP and WebSockets. This we'll be able to run that in Node and Go. WebSockets we'll be able to add to the browser. And then on the JS side of things, we're going to add WebRTC. And so what WebRTC is going to give us is the direct browser-to-browser communication. And then it's also going to give us the ability to listen on this signaling server.
Can I ask you a question?
Mm-hmm.
You're mentioning that WebRTC is good for net punching without stun server? Or do you still need to use a stun server to have access to the WebRTC magic?
So you still need a stun server. However, we are in progress of building, working on a spec to create distributed signaling servers. So giving any node the ability to run a stun server for you. So as long as you're connected to a node, you could use that node as a signaling server.
That is really super good.
Yeah, so hopefully that will be one of the things that I work on right after camp.
Interesting.
So this is when we would break and go into configuring transports. Because we're on a compressed timeline, we'll skip over that. But as you're going through that, if you do this on your own or you're doing it right now, following along, if you do get stuck, you can look at chapter 2 and it will have all the solution code for you. We're likely going to go through and we'll probably stop at chapter 4 and walk through some of that code because the protocol code is a bit more complex. And then we'll make some time at the end to go through the more complex messaging protocol. So once we have that initial transport configuration, we want to create our first connection. This is typically going to be to a bootstrap here. So for us locally, this would be this bootstrap node that I'm running on my machine. For IPFS, those are our gateway nodes. And typically with IPFS, what we have is we have a list of 10 known gateway nodes, and we dial directly to those when we start up, and that lets us bootstrap into the network and we can find peers from there. So in order to dial to those, we need to know the address. So this is where multi-addresses come in, commonly referred to as multi-adders, because E's suck. So what multi-addresses do is they let us compose flexible addresses. As a species, our communication has changed a lot over time, and the address of those forms of communication has changed. Postal addresses, email addresses, phone numbers, domains. The format of those has changed over time. So what we need to do is we need to create a flexible mechanism that we can describe addresses over time as we get Bluetooth transports, if we get radio transports, whatever those look like. How do we make sure that we have a flexible form of describing that? And that's what multi-addresses aim to do. So let's look at a few of those. So if you run an IPFS server, you're likely going to see the very first address pop up, which is a TCP address running on your local IP on port 4001. So if you want to dial that node, you have to have local access to it. The second one, almost the same, is running on port 4002, but there's a WS at the end, which is WebSockets. If you see WSS, that's WebSocket Secure, so it's the SSL version of that. And it also tells us that the WebSocket is running over a TCP transport. Potentially in the future that could change, and maybe it's not TCP transport at the beginning, and it might be something else that WebSocket runs over. So let's look at some fun ones. This one up top is a WebRTC star address, which we'll be using today. And these are best, I've found, to read from from the right-hand side, because we pick up what the target node is running over. So here we see the target node is running PTP WebRTC star. That's our signaling server address. So this indicates that whatever we're about to dial is running over it's listening on the signaling server. So then we can see that signaling server's address is a WebSocket address over TCP on port 15555. The next one, a bit more complicated, is a circuit address. So this means we're running over a relay, a circuit relay. The ID of that relay is P2P, QM relay. So this is an abbreviated version of your QM IDs. If you look at multi-addresses in the wild now, P2P will probably be IPFS. The goal is to move to P2P. It's currently supported in both JS and Go, and it will fall back to IPFS. But because when we built it, it was very specific, more like IPFS, but no, anybody can use that. Any libp2p node can use it, so we use P2P. And then we see that that relay server is running over the quick transport, which runs over UDP on port 4001. Super easy, right? So once we have that multi-address, we can set it up and actually dial to our peer. The multi-address tells us a lot about our peer. Most of the time, we're going to enable multiple transports to our peer, so we're going to get a giant list of potential multi-addresses, which is a great thing, because the more transports that we have and we support, the more people can dial us, assuming our addresses are public. So chapter 2 is going to be focused on just adding that. So if you go into the code, it's just going to be, you're going to add your listening addresses if you can. And luckily, mostly everything will be able to add listening addresses for, because we are using the signaling server. And then the dialing addresses, which will dial to the Bootstrap node. For you locally, there is in the Node.js folder, and there's a Bootstrap folder in there, which has the Bootstrap node and a signaling server. And so if you run that locally on your own, that will, the examples will automatically dial to it, because they're set to dial to the local port. So when you do that, this is what happens over Wireshark. This is the connection. So the only thing we see here is our node dialing to the port of the Bootstrap node. And the only information that we exchange is a multi-stream handshake. This is our protocol negotiation handshake, which we'll talk a little bit more about multi-stream in a bit. And then we see plain text, which is our very, very secure encryption library. We'll go into encryption more in a little bit. But this is it. It stops. Like, there's no more data that's exchanged. We're connected. So how do we reuse that connection? If we have this connection, libp2p wants to do a bunch of things in the background. It wants to do a bunch of exchanges to verify things. But when we don't have a multiplex connection, it's hard for us to do that. It's painful for us to do that. So we want to be able to reuse that connection. We've got pub sub messages, DHT queries. We've got the libp2p identify protocol. There's direct communication. The chat protocol that we're going to write for this, we want to be able to use that too. How do we reuse the connection there? How many of you are familiar with the tin can phone? So it's the idea that you can take a can of your favorite foodstuffs, punch a hole in the bottom of it, run a string to the other can, and you can talk with somebody in the local room.
Do you have a transport for that?
Nah, not yet. Maybe someday. Maybe it'll be at the science fair. Run the BPO over tin can. Very reliable on a network like today. Yeah. So how do we get from here to something like this, but without multiple connections? What if we had one connection that did a bunch of virtual streams? This is what stream multiplexing is for, commonly referred to as muxing. So multiplexing, it's not a new concept. They actually used it in the 1870s for telegraphy, so it's been around for quite a long time. If you think about TCP connections running over an IP address, those are multiplexed by port. Telephone lines multiplex phone calls by historically by frequency of the phone. So if you were calling your neighbor down the road, it would operate on a different frequency than somebody else using the line. And as soon as we had too many people living in a space with not enough lines, eventually we ran out of frequencies and we had to add more telephone lines. libp2p multiplexers don't work the same way, but they do a similar thing. So for example, multiplex or mplex, it does this by prepending data in the stream with the stream identifying header, as well as the length of the content that you want to send. So when we go in and we send a chat over the wire, we say that chat message is 100 bytes. What we do at the very beginning of that, we say, okay, let's create a new stream. We'll call the ID of that stream 5. We're going to send a message of 100 bytes, so we say it's going to be 100, and then we tack on our message. We send that over the wire, and when we read that in, we say, okay, this data is going to stream 5. There's 100 bytes of it, so I'm going to read the next 100 bytes, and then I'm going to stop, and I'm going to pull that in and send it. This way I don't chew in to the next message on the stream or on the connection, because it might be going somewhere else. So muxers that we currently have available, mplex is the most widely supported. It's in JS, Go, and Rust. Yamux is in Go and Rust. Speedy, JS and Go. Quick has a built-in multiplexer, so only Go has that support right now. And then Muxado is also in Go. Again, you can bring multiple multiplexers to libp2p. You can configure multiples of those. The advantage there is perhaps not all nodes are going to speak the same thing. Like we talked about, a varying degree of support here, and some multiplexers are more performant than others. So if you bring multiple multiplexers, you're going to have more options going forward. This also helps with upgrading network over time. As we add support, we can slowly deprecate support rather than cutting off a huge chunk of the network. So chapter 3 code is going to focus on both muxing and encryption. But let's take a second and go back to Wireshark and look at what happens if we just enable multiplexing. No other change in the code. This is what happens. If you see up on the right-hand side, there's a scroll bar. So we still have our multi-stream handshake, and then we have our super secure plain text, and then we negotiate mplex, which is our stream multiplexing. As soon as we do that, a bunch of crap happens. We negotiate circuit relay, we send over IDs, so we're letting each other know what protocols we support. We're negotiating DHT relays to determine what we support. Ideally, this would be a lot shorter. Right now, the multi-stream 100 protocol negotiation is pretty inefficient. We have specs that we're working on for multi-stream 2 that should hopefully make that much shorter so we can get all the information we need in much less conversations. But yes, this is just enabling multi-stream, the multiplexer. Something you'll notice here, all of this data is free to look at over the wire, not the best. Our plain text is failing us. So how do we encrypt that data so we can see it anymore? Luckily, libp2p, you can bring whatever encryption framework you want. Currently, SecIO is our most supported. That's supported by Go, JS, and Rust. TLS 1.3 has support for Go's out now. As we get more support, we'll likely migrate away from SecIO over to TLS 3 or one of these other encryption. Some people are working on noise for that, and then the quick transport also has built-in TLS encryption support. We originally built SecIO, just as a quick history overview, because of needing central authorities to do certificate generation. That doesn't work very well in a peer-to-peer distributed network. So we rolled that until TLS 1.3 comes out. And I believe it's almost there for JS. So hopefully we'll have that soon. And again, chapter 3 will deal with encryption. So as you go through chapter 3, it will have stream multiplexing added in there and encryption. And if you get stuck at any point, check out chapter 4 for the protocols. Now, if we go back to Wireshark to look at that, we'll see multi-stream. Plaintext is gone. We now have SecIO data exchange, and then after that, we have some nonce
exchanges, like 24 or 32 bytes, and then everything gets encrypted after that, after our original identity exchange. So Wireshark can't parse that anymore, so everything is secure. Yay! So now that we're encrypted, we've been talking a lot about protocols in libp2p, this multi-stream 100 protocol. There's an IPFS ping protocol, there's a circuit relay protocol. So what the hell are protocols? If you think about like a RESTful API, if you're familiar with RESTful APIs, you can think of protocols like endpoints or paths in your system. And ultimately what you're going to do is you're going to register handlers for those paths. Multi-stream 100 is like the router for that. So ultimately it's deciding about how our API is going to work and how we're going to negotiate those. So just like in a RESTful API, if you try to send data to one endpoint that doesn't exist there, it's not going to work. And if it tries to send you data back that you're not expecting, your application is probably going to have a bad time. So just, if you're familiar with REST, think about it that way. So we're building a chat app. We should create a chat protocol. And we'll go ahead and call that libp2p chat 100. Something to note, when you're building protocol names, if you're going to be joining the public network, be descriptive. If you just pick something like chat 100, even libp2p chat might have a bad time. If you're connecting to millions or billions of nodes, there's probably going to be some conflict there because you will try to negotiate at some point in time with other peers. So yeah, just be descriptive, just like you would namespace any code packages or domain names. So, chapter 4, Cole's not here to help with the Go stuff yet. So what we'll do is, I at least want to go over what the protocol is and quickly look through that. So what we'll do is, I'll just pull up some code here for the JS. And if you want to follow along on the Go code, feel free to do that. All right, so if we look at Node, in here, I'm in chat, Node.js, going to the protocol. So the chat protocol is pretty simple. All we have built so far, can everybody see that all right? All right, so we have our chat protocol string, chat 100, and then here is our handler. It's pretty basic. If you go through the browser code, it's going to be almost the same. There's just some view differentiation in how we're setting stuff up because it's React versus printing to the terminal. So in here, registering our handler for JS, it requires takes two arguments. One is the protocol. Right now we're not using it at all, but what this lets you do is actually do like match functions and things. So for example, like in IPFS, we have bit swap 11 and 100. What we can actually do is use this protocol information to figure out what version it is and then do like case-specific checks. So if we have 11, then we can run a different set of code than 100. And then we're just taking the stream that we have here. Then all we're doing, if you're not familiar with pull streams, is this is basically a pipe. So we're taking the stream and we're piping all of that data into a collect and then just logging it out to the console. So all we're doing in the browser is setting that on the React component. So it's just a very super simple thing. And then the only other thing we have here is a send method. So when we go to dial this, we'll show you the dial code in a second. It's very crude, kind of gross, but we'll improve that later. Is this send function, which just takes the message and it pipes it over the stream, and that's it. So if we go look at that code, let's go to chapter 5. So chapter 5 has all of our solution code. So in here, all we do is we do a libp2p handle call, and that's going to take our protocol and our handler function, and that's it. And if we had multiple support, so say we had another chat protocol, we could do libp2p / chat / 1.0. If our handler did that check on the version number, we would be able to do this and just let the chat handler code multiple versions. Then all we're doing is we're reading in the terminal data, getting rid of the new line character, and then the very gross thing that you probably don't want to do in a real world scenario. Yes?
Just a quick question on the handler callback function. For protocol, is it like exact matches only? There's no wild cards, or
Well, this is what you get with the,
just do
if we go look at the chat protocol, this is what you can do here, is you can do
so you would just do multiple
version
calls
checks.
to.
Yeah, to register the handler. You
Yeah.
can do, right now it's specific in the JS code to do multiple handler version calls, because every time you go through and you call the handle code, it's going to take that and it's going to add it to your identity information. And when you do an identity handshake with another peer, you're going to tell that peer about all of the protocols that you support, including the version changes. And what that lets a peer do is make more informed decisions. So rather than blindly dialing you and checking a protocol and wasting that round trip, they can just say, oh, you don't support 1.1, you still support 1.0, I'm going to just dial on that 1.0 handshake. So here, the crude code that we're doing right now is we look in our peer book in Go. This is called a peer store. We should probably coalesce on those names. All we do is we get all of the peers, we check if we're connected to them, and if they support the chat protocol. This is our check that has. And then we dial to them and negotiate the chat protocol. And if we connect, we send them that message. This is super gross, right? Because it's like, all right, we're all connected, 40 of us in a room. I'm gonna make sure that I dial to every single one of you and send you a message. Like this is painful. So how do you make that better? Not that. This one. So the first step into making that better is to actually find peers instead of manually targeting all of them. Like, hey, let's all exchange address books and write each other's IPs down. That sounds awful. So how do we find peers on this very giant network? We can talk about a few of these, but libp2p has support to build your own peer discovery network. So if you're toying around with Bluetooth or NFC or radio or anything else, you can build a discovery transport for that and just plug it into libp2p. So the first 4 that we're currently going to be using in this workshop is Bootstrap. Bootstrap is a discovery mechanism that all it does is say, hey, you have a list of multi-addresses. I have just discovered those peers. Now you can dial them. That's it. It's very crude. But for a network to be able to progressively make its way to being fully distributed, this is a decent centralized approach to getting there, at least in the interim. MDNS, or multicast DNS, is local network discovery. So if you think about printer, discovering a printer on the network, or the old Mac Bonjour app, finding people in the local network, that all uses MDNS. So ultimately what happens is you're going to connect to the local network. You're going to use the libp2p lookup to look up libp2p services on the network. And then every other libp2p node is going to respond back to you. And you're also going to reply to that query. The advantage of this is when you join the network, you're also going to be broadcasting your new identity to the network so people can connect to you. If you look at the visualization, there are going to be some people running this. There are also just people that I'm finding on the network because I'm running Node.js and the MDNS service. So these are just random people that are on the Lenovo Wi-Fi that are also running libp2p. So we do see a couple of nodes there that are part of our chat client. The green nodes, which are Node.js, I believe. There's a legend up there. And the purple node is Alex. So if you do make your way, or you happen to jump into the chapter 8 and start that up, you should be able to chat with Alex if you join there or running MDNS. So the DHT we'll talk about right after this because it's a bit of a thing.
but we'll talk specifically about the random walk component of that. And then we have rendezvous servers. So for this, we're using the WebRTC signaling server. We also have a WebSocket rendezvous server. Not only does the WebRTC signaling server allow us to negotiate and get direct dials, but it will also tell us about every other peer that's connected to it. So it also acts as a peer discovery mechanism, which is nice. So let's talk about the DHT random walk. This is a very useful discovery mechanism once you join something like the Bootstrap nodes. So the way the DHT random walk works is ultimately you're going to do a query on the DHT. If you're not familiar with the DHT, it's a distributed hash table, just a big fancy key value store, basically. So what we do is we're going to create a random peer ID. We're not looking for anything specific. We're just going to create a random ID because we don't want to find anything on the network. We just want to find other peers on the network. So we create a random ID, and for simplicity, since QM IDs are hard to keep in your mind, we'll just say Brandon. So we create a random ID of Brandon. We're going to look for that peer. So the first thing we do is we look at all of the peers that we know. Are any of them Brandon? Hopefully not, because we just made up this ID. If we got that kind of collision, we'd have bigger problems, but we shouldn't get collision like this. So what we'll do is we'll look at all the peers that we know, and we're going to find the peer with the closest ID to Brandon. So this is eventually going to be a DHT key, and what we do is we do an XOR binary check on that to see what the bit difference is, and the smaller the bit difference is, those are the peers we're going to use. So if we look at our group of 6 here, we check our 5 peers, and we see that Alice and Bob have the closest IDs to Brandon. So we'll go ahead and say, okay, I'm going to query Bob. Bob, do you know Brandon? Bob says, no, I don't know Brandon, but I know Brenda, who has a closer ID to Brandon. So this is how we discover Brenda. And this is how the DHT random walk works, except at a much larger scale. Like a DHT random walk query is probably going to query between 100 and 200 peers. Yeah. So we're going to continue down that query until we can't find anybody that's closer. So this is why we end up querying so many peers, because we just keep asking and asking and asking. The JSDHT will query 40 peers in parallel right now, because ultimately we don't go down one path, we go down many paths, and we do that recursively until we get no better results. So, just like transports and multiplexers, discovery works best when you bring many of them. If you just bring Bootstrap, you're probably going to end up here, the first one. Like, yeah, we know this Bootstrap node, that's not super helpful. Let's add MDNS. MDNS, we get local discovery, so all the peers that we know will now get access to the network. And then rendezvous server can let us do stuff like just WebRTC signaling. We can get NAT traversal, we can actually start talking directly to people. So ultimately we're trying to get here. Right now, the internet is here. So, chapter 5 is going to show you how to set up that discovery. It's pretty simple for all of those. It's all basically just configuration and adding in a couple modules. If you do get stuck there, or you want to look at that towards the end here, we can go through that code. And again, the solution will be in chapter 6. You'll be able to see that solution code. So, we talked about the super gross style everybody code to chat with them. Let's not do that. How about we use PubSub? PubSub seems like a good thing to use for chat. Currently, we have 2 PubSub libraries. There's GossipSub or FloodSub. So FloodSub is a very, very crude, simple, inefficient version of PubSub. What we do is we take every peer that we know, who's a PubSub peer, and we send them a message. And they take that message and set it onto every peer that they know. And we do that over and over and over and over again. We do add a cache, so we don't continually flood the network. But it's crude and it's gross, but it works. It works very well. People will get that message. Hopefully not multiple times, but it does happen. So GossipSub is a better version of this. What GossipSub does is when we connect to a PubSub network, we take a subset of peers. So maybe there's 20 of us in the room. We'll take maybe 5 peers, and we create an overlay network with those pub sub peers, a mesh overlay. And what happens is whenever we get a message, we only send it to those peers. When we subscribed to those peers, we also told them that we were adding them to our mesh so that they can add us to theirs, so that they'll also send us messages. The problem with this approach is peers might not get messages, right? We're only broadcasting to a subset. This is where the gossip component comes in. So what we do, in addition to sending messages to our mesh, is we pick random peers who aren't in our mesh, and we broadcast them metadata about recent messages we've seen. So we might say, hey, I've just sent these 5 message IDs. And they'll say, oh, I haven't seen 2 of those. Give me those messages. They'll get the message from the peer, and then they'll broadcast to their mesh. So this is how we overcome that issue. So it's a more efficient version of gossip sub. So why would you use flood sub? Support right now is the only real reason. Currently, JS and Rust have implementations in progress. Hopefully we'll get them soon. So this is why you would use flood sub. The advantage for all you Go folks is that you can use gossip sub right now, and it will fall back to flood sub for all you peers who don't speak gossip sub. So win-win. Yeah, Go. Yeah, so chapter 6 deals with getting rid of that super gross chat client code, and we'll look over that at the end. I just want to make sure that we get through the rest of the content, and we can go over what that transition looks like and how we just switch over to using PubSub. So part of PubSub is going to introduce messaging, like protobuf messaging. So we're chatting over PubSub. That's great. We actually are exchanging messages using protobuf. If you're not familiar with protobuf, it is a data serialization, deserialization library, just like JSON or CBOR. You don't have to use protobuf. You could use JSON or CBOR. Just most of the libp2p protocols today currently use protobuf. What protobuf lets us do is take data objects, serialize them, send them as binary or bytes over the network, and then turn them back into objects, and that kind of looks like this. Currently, we were just sending, in chapter 6, we're just sending messages over the network. That's not terribly good use of like one protocol. So how can we make this a little bit more complicated? Well, in libp2p, we do this with protobufs. So you can see here, as we're using in chapter 7, in the no code, the JS code will also have an extra request type. So we add request types here. The first one you'll see is send message, and that's just our basic message data that we're sending. This is our data, our chat message, when we created it, and then a very basic ID for the chat. We also do an update peer request. So we add the ability, if you are using chat, you can do, and you are in chapter 8, you can do /name and rename yourself. While this isn't a terribly good way to change your name, because if anybody joins PubSub later, they're not going to get your name changed, this at least shows you how you can go about doing multiple request types. So we'll look through that code at the end here and see how we're handling the different case of the request type coming in. So we'll go over that shortly as part of chapter 7. We'll walk through that code. But quickly, we're going to talk here about subnets. So we have our chat protocol. We want to chat with each other. Say there's 30 or 40 of us in this room. Now we all go home and we want to chat with each other. If we join the public network, how do we reliably get chat to one another? If there's a network of millions, how do we make sure that the 20 of us are getting each other's messages? Do we go back to this thing and manually dial each other? Or do we just use PubSub and hope that our chats make it across the network to one another in a timely fashion? Probably neither of those. So we can actually go back to the DHT. In addition to being able to find peers and storing peer information,
DHT also stores content provider information. We store provider records. So an approach to this, not the only approach by any means, but an approach to solving this subnet problem is we could use the DHT, this similar concept to the random walk, to store a provider record. So instead of randomly querying for an ID, what we could do is take our chat topic, libp2p chat 100, we could turn that into a DHT key and do a query to find the closest peers to our DHT key. So we go out, we do that random walk that's no longer random, we find the closest 20 peers on the network to our topic, and then we tell them that we're a provider of that topic. So when we subscribe, we can broadcast that, we can set it, we can also query to find other people who are providers of that chat topic. So we could go query out to the network, find that information, now we can dial each other. What this gives us the ability to do is we can create a mesh overlay, chat overlay network, in addition to being connected to the broader network. And this is going to be an important part of distributed systems, because if you just blindly connect to the network and broadcast information, you're probably not going to be able to reliably exchange the information that you want. Ultimately, in a distributed network, we need to be able to create areas of concern or things that I care about. I want that information, so we want to create overlay networks. This is a possible way of doing that. So we can take our chat topic, register, unsubscribe, and query unsubscribe, and then create overlay network. There's not any code currently in libp2p that manages overlays, but that is something that we probably want to look at. And I think we're doing a deep dive on connection management later today. So if anybody's interested in that, come join and we can talk about that. So that's the end here. We have 9:15. All right, we've got like 20 minutes, so we can go back and walk through some code. Does anybody have any questions on any of the topics before we do that?
I understand this is all scope for libp2p, but does standard IPFS know, like, is it just able to run this stuff also? Like, does it have libp2p in the back and I can just use that?
Yes. Yeah. So there, Brendan B5 talked about this in his lightning talk yesterday about getting access to like the host in Go to be able to do this. Okay. In JS, you can just access the libp2p object on it. If you are running like a daemon or you're running CLI, you would have to look at another way of doing that. But if you're running the IPFS code, you can get access to the libp2p object and
And similarly, I can talk to anyone who is basically and stuff like that.
Yes, yeah. So these might be IPFS nodes, not just libp2p nodes.
Another question about this approach of using a DHT to find people interested in a topic. I don't really understand why I have to go to the DHT. Isn't that exactly what Gossip Sub is supposed to do for me? Like I say, I have a topic, I want to have only, or want to communicate with people that only are interested in this topic. Isn't that what Gossip Sub is supposed to do for me?
It should do that, right? It's getting to the peers on the network.
I noticed some difficulties there as well, but at the end of the day, you would expect that any interaction with the DHT that's necessary would be done by Gossip Sub. So Gossip Sub, please make sure I can communicate with people which are interested in this topic.
Yeah.
So you shouldn't have to go all the way to the DHT as an application developer, I would say.
Yeah.
Sometimes it's necessary, but
right. And ideally with and I think that's something that we want to add to libp2p in general, because not everybody's going to be using Gossip Sub for what they need to do. So how do we create those overlays in general for libp2p so that application developers don't have to worry about that? So that's something that we want to work on as well, so that we get that mesh overlay behavior that Gossip Sub has for other content that's not Gossip Sub.
So I'm trying to get one question answered for myself. We have a product with two devices owned by the same user. One is the computer, the other is a mobile phone. The computer is running in the browser.
Yeah.
The phone is running on React Native. We need to transfer button data between them. Can we easily, without requiring the user to install anything else, get them to connect and to exchange data, or not?
Yeah. So you have mobile device when they're offline, or
And the bottom line, so we could do QR code with some discovery, but they need to somehow talk with each other, and they could even be on the same network.
yeah. So you're not going to be able to use like MDNS unless because if you're running in the browser, that's going to be a problem. There is stuff that we're looking at with like Bluetooth, but most likely you're going to have to go through an intermediary server to discover one another. Currently at the moment, yeah. Until we've looked at Bluetooth support for being able to do that locally, but browser support is not quite there.
So what if I'm running a Node.js client on the computer?
Yeah.
Is that possible? Okay.
Mhm.
So,
You have implementation of MDNS in React Native.
Okay.
I used them last week, so they work.
that's cool.
Another question.
But
So
you use React Native, you said.
sometimes
So-
there is a
so
situation where you
I
can
mean,
connect to
just
some
to
nodes
choose
using one
MDNS.
transport and some other nodes using another transport.
Yes.
For example, you're on the local network, you can only connect to local people using TCP transport,
Mhm.
but or to the cloud you can only go via WebSocket, WSS, because corporate firewall. Is there a way to basically, based on the node, somehow select the transport, or is it just you configure the transport? Somehow?
Yes, and so this is how multi-addresses work. So let's take a quick look at these. So here, we've registered for our peer that we are listening on TCP, we're listening on WebSockets, and we're also listening on the WebRTC star server. So we're gonna broadcast these addresses out to our peer. This also looks like, if you look at the Bootstrap node, ooh, lots of messages. We have this series of addresses here. So we're gonna advertise those addresses to all the peers, and ultimately what we do is, when we take those addresses, libp2p is gonna go through them and it's gonna filter for transports that it supports. And then it's just gonna dial over those. So you automatically will get, this is why bringing multiple transports is valuable, because even if you're just dialing over them, that we can go through and say, okay, well, this is TCP, maybe I don't support TCP, but I do support WebSocket, so I'm gonna dial to you over WebSocket. I'm gonna try that one first. And then it will just keep trying the addresses until it succeeds. Various versions. JS currently will do this in serial because closing open connection dials is painful right now in JS. But Go will try all of the addresses in parallel. So it will attempt to dial all of them, and the quickest address is the one that gets used, and then we coalesce on the address.
So if you configure some node as a WebSocket support, then it should work out of the box, because it will advertise that it supports WebSockets. People will try TCP and WebSocket. TCP won't work, but WebSocket will work, and then we'll drop the TCP thing, right?
Yes. Yep.
Okay.
So if we went and let's look at PubSub. So when we switched over to PubSub, we created a basic PubSub chat topic, or a PubSub chat object. And we changed over when we got our message, rather than doing the protocol send, we now do a PubSub chat send. So if we go look at our new PubSub chat type, we've got our protobuf here. And if we go down to send, we'll see here, we're doing an encoding of protobuf with our message data. And then we just do libp2p publish on PubSub. And we're doing it to our chat topic. We send the message, and that's it. Logging out any errors. And then as messages come in, we go in, we decode the request, we get the request type, and then based on the request type for our protobuf, we can just do a basic switch to figure out what we need to do, whether that's setting a user handle for people, or going through and actually firing off that message handler, whether it's to our React view or rendering that out to the terminal. Does anybody have any questions about it? So what we'll be doing as a follow-up to this, because it is a lot of content to jam into 75 minutes,
we're going to be putting together some videos of each of the chapters and just kind of creating a video series. All of the slides will be posted. There's a bunch of speakers notes in the slides that walk through everything as well. And then you can check out the README. So we'll go through and actually walk through the code, so you guys can, if you want to dive in and get more hands-on with this outside of context or outside of the chat, feel free to do that. And we'll have those, hopefully have the videos posted in the next few weeks.
Thanks a lot.
And if you have any questions or want to talk about anything or want to spend the last 15 minutes or so, otherwise I'll let you have that time back and recuperate and chat.
I have to go to programming session, but I will answer your situation later.